There are four factors affecting reaction rates. Number 1, concentration. Number 2, particle size. The third one is catalyst. And the fourth factor is temperature. In this STR8CHEM session, we're going to look at the factor of particle size. And to start, let's have a look at the situation we have in front of your screen. Suppose we have 3 conditions of the same compound. Condition number 1, when you have it 5 grams of the compound as a single particle. And then in the situation 2, you have divided the particle over here with the same mass, but it is divided further into 1, 2, 3, 4, 5, 6, 7, and 8 parts. And in the third situations, the same mass of compound is divided further to make it even smaller pieces, and you have that in this condition. Okay, first of all, you need to realize that condition number 1, 2, and 3, all of them, they have the same mass, 5 grams, 5 grams, 5 grams. But the difference over here is, number 1, you have a single block of particle here. Number 2, you make it even smaller pieces. And number 3, you make it into even smaller pieces if you compare it with number 2. So which one has the highest reaction rates, do you think? Maybe you want to spend a few minutes or a few seconds to think about it. Is it number 1? Is it number 2? Or is it number 3? If you think that the answer will be number 3, this one is going to be having the highest reaction rates, you are absolutely correct. Okay? So the reason why condition 3 has the highest reaction rates, it's because if you compare 1, 2, and 3, condition number 3 will have the greatest surface contact area exposed for reaction. When you make this particle over here, this 5 grams of this particle over here, into a much smaller pieces, you are making the surface contact area that will expose to reaction even bigger. We have an example over here with magnesium solid plus hydrochloric acid to make MgCl2 and hydrogen H2 gas. So you can imagine that the magnesium lump, a big piece over here, one huge piece of magnesium lump, same like the situation over here, you have one huge particle. In this condition right now, the magnesium solid will have very small surface contact area. You can see that the red dots over here representing the HCl that wanting to react with your magnesium. So the green balls that you have right there representing the magnesium solid, and only the magnesium particles on the outer side of it will be reacting with the hydrogen ions or with the HCl outside. Okay, so the red one over here representing the hydrogen ions that want to react with your magnesium lump. So the one that is inside, okay, but the one that is inside will not going to be able to react with the hydrogen ions coming from your HCl. So you have the outer layer to be reacting, but not the one inside. So that is what it meant by smaller contacts of surface area that exposed for reaction. But what happens if we're going to break the magnesium solids into smaller pieces? So what happens if we do that? So if we do that, we're going to have a totally different situation. Now you have broken down the magnesium lump solids into smaller pieces, and right now even more magnesium solid will be reacting with your hydrogen ions coming from your HCl. So in this condition, now you have greater surface contact area that will be exposed to reaction. Okay, so what you see here is, in that condition, you have smaller surface area and exposed to reaction. And the one in this condition over here, you have, okay, so you have that and you have that one. They have larger surface area exposed to reaction. So basically, the smaller, okay, so when you have smaller particle size, the surface area exposed for reaction will be bigger. So when you have smaller particle size, you have bigger surface area exposed to reaction. And what happens to the effective collision? So effective collision, the frequency for effective collision will increase, okay, will increase, and the rates of reaction will increase.